Okay, so here's what we have left. We have kind of started thermodynamics yesterday and basic idea gas laws and thermal expansion. And that's all just basically a function of energy. So today we're going to start kind of like this big 2-day lecture that's going to take me today and tomorrow to get through. So I'm going to give you like the assignment today, but it's not going to be due until Monday. So mainly because we won't get through all the stuff that you need to know to be able to work the whole thing, but if you wanted to, you can get like a head start on it. So, but it won't be due until Monday. So there's that. So we got that today and tomorrow, and then Monday we do buoyancy, Tuesday we review, Wednesday we take the big test over like this kind of random thing of thermodynamics, buoyancy, energy, gas laws, and then have a written final, and then hopefully a 3-day lab final, and then when we're done and life will be good, and there you go. Okay, so let's talk about this concept of this ideal gas law, which is PV equals nRT. So let's start with this. So here's the deal. If there's anything that has an identity crisis in science, it's pressure. But no matter what, whether it's PSI, whether it's pascals, whether it's atmospheres, whether it's bars, whether it's inches of mercury, it doesn't make any difference. The whole idea is that pressure is created by these tiny little bits of matter, oxygen and nitrogen mostly in our atmosphere, that are always colliding with us, okay? And everybody has this idea that, oh, pressure only pushes down, okay? It doesn't. Pressure pushes in all directions, because if pressure was only pushing down on the top of the tables, it would collapse, okay? And it just, you couldn't have it. So this pressure is all around us. Now, it does change based upon height. So if you've ever driven like to Colorado or gone up to the mountains or flown in a plane, your ears pop. You can feel that pressure differential. So yeah, as you go higher and higher and higher, the pressure becomes less, because it's kind of like if you've ever, like a pyramid, like if you're standing on if you're making a pyramid of people, well, if you're on the bottom of that pyramid, you have a lot more weight on you than the person does up at the top. So since we're at the bottom of this atmosphere, that's why we have all of that weight up above us pushing down. So to give you some idea, that pressure right now is 101,300 newtons per square meter. Okay, so that's the atmospheric pressure that we're on right now, which is equivalent to about 14 pounds per square inch. So what that means is if you take Hank the bowling ball, okay, so Hank weighs about 14 pounds. So it's pretty hefty. So that's how much pressure there is on every square inch of your body. The equivalent of Hank pushing down on every square inch of your body. And don't flip out and go, oh, I feel that. Okay, no, it's cool that we have that, because if we didn't have that atmosphere, we wouldn't be here having this discussion. So it's vital that we have that atmosphere, because otherwise we wouldn't have weather, we wouldn't be able to breathe, we wouldn't be protected from the sun's rays, all of this stuff, okay? So it's good that we do have that pressure. But what's creating that pressure is tiny, tiny, tiny bits of this matter, oxygen and nitrogen, that are bouncing around, hitting us. And every time that hits, it bounces back. When it bounces back, that's what creates pressure. So, from a physics perspective, that pressure, and this is where everything has to work out, if you look at the units, get rid of all of this, so that pressure is newtons per square meter, okay? So your volume's in cubic meters, that cancels out, you get Newton meters. Newton meters is the same thing as joules. So on one side of the equation, you're generating joules. On the right side, you have moles, right? You all have done Chem 1. You all studied the concept of moles. Then you have the gas law constant, and that gas law constant is here on your equation sheet. Up here, 8.314 joules per mole Kelvin. So that's joules per mole Kelvin, and then that temperature has to be in Kelvin. Everything cancels out. You get joules on both sides of the equation. Hey, we're golden. Okay? Now, what's going to happen is when you change those values, like pressure, volume, temperature. Those are the big three that you're going to change: pressure, volume, and temperature. So the easiest thing to do is to keep the number of moles the same and the gas law constant the same, and go P1 V1 over T1 equals P2 V2 over T2. Okay? So this will get you through 95% of all gas law problems. Just this relationship right here. And what you do is you just cover up the ones that are going to stay the same. So if you look like on question number, which one is it? Like question number 9, okay, on that assignment. So you've got cars typically pressurized to 2 atmospheres at a temperature of 20 degrees. What will be the new pressure if the temperature is raised to 40? So what's going to happen on that one is that you're going to keep volumes the same. Okay, so I didn't give you the volume, so you couldn't work volumes in here if you try. So the volumes are going to stay the same, so you don't have to worry about that. So that leaves you P1 over T1 equals P2 over T2. Now, what has to happen, okay, your temperature has to be in Kelvin, all right? Your temperature has to be in Kelvin. Now, let's just think this through, and this is where you can visualize this in terms of second graders, all right? So, on number 9, you got 2 atmospheres at 20 degrees. What's going to be the pressure if the temperature is raised to 40 degrees Celsius? Now, think about this. Visualize you're a second grade teacher. And pressure is created by these little second graders running around and running into your ankles, okay? Because they're not very tall. Okay, maybe they're your lower legs for certain. And that's what's creating pressure, okay? Is these little particles running around and hitting the sides of your legs. Now, all of a sudden, the size of the room isn't going to change, okay? So imagine the size of the room being the volume, okay? So we're going to keep the size of the room the same. But mom shows up, and it's Timmy's birthday, and she gives all these kids an extra bag of Skittles, okay? So now they've had their Skittles. It's like, oh my God, wow, okay? They're going to flip out. So now they're going to have a lot more energy as they're bouncing around. So that's one of the cool things that we've done as a species, is being able to figure out how to measure temperature. Because at the end of the day, temperature is a reflection of how much energy the Timmies have when they run into the temperature sensor. So you all have, like, done labs where you've measured the temperature of water, right? And basically what that is a reflection of is how much energy the little Timmies have when they hit the temperature probe. So the Timmies have a lot more energy. So you got to figure, oh, I'm going to feel more pressure. Because when these kids are colliding with your legs, your pressure can go up because of one of two things, or both. Your pressure can go up because you're having just more collisions, okay? So there's more kids in the room and you're getting more collisions, so that's going to make the pressure go up. Or the kids have more energy when they do collide with you, or it's a combination of both, okay? You have more collisions and they have more energy. But that's what you are going to feel. So that's what pressure sensors monitor, that collision with those particles. So if you look at what's going to happen, so if you just do a simple cross multiplication and go, okay, pressure 1 times temperature 2 is going to equal pressure 2 times temperature 1, okay? So now in this situation, because I don't actually tell you to change it into newtons per square meter, you can actually leave the atmospheres in atmospheres. If you want to change it into pascals or newtons per square meter and multiply by 101,300, that's cool. You can actually just leave this as pascals if you wanted to. But here's the bigger idea. So your first pressure was at 2 atmospheres. Now, your temperature has to be in Kelvin, okay? This is the one thing that is an absolute truth. Your temperature has to be in Kelvin, okay? Which is a simple conversion. You just add 273 to it. So that first temperature is at 293 Kelvin, okay? So I'm going to have some pressure, okay? 2 atmospheres. And 293 Kelvin. So now I'm gonna raise that temperature to 40 degrees. So now my second temperature, right, is gonna go up. So it's gonna go up to, I'm gonna take 40 and I'm gonna add 293 to it, or 273 to it, and I'm gonna get this new temperature. So just think about this. At a higher temperature, these particles, the little timmies of the world, are going to have more energy. The pressure is going to go up because these kids have all been given Skittles, okay? And now they're flipping out, they're bouncing around all over the place. So imagine that you're teaching a second grade class. Here's all these kids with Skittles, okay? You're going to feel more pressure. So you know your answer has to be bigger than 2 atmospheres, okay? You can think of it conceptually, or you can just look at this in terms of mathematically. Oh, okay. Well, if my temperature goes up, to keep these 2 sides equal, my pressure has to go up. Okay? So I don't care how you think about it. You can think about it mathematically, conceptually, whatever. But your pressure is going to have to go up. Okay. And then on the second one, you're going to drop that temperature down. So you've removed energy from the kids, okay? It's like, sorry kids, no Skittles today. The kids going, oh, bummer, okay? And they're all sad, so you're going to remove energy from them, so they're not going to be as happy, so you're not going to feel as much pressure, okay? Got that idea. So on number 9, this is in atmospheres, okay? That first atmospheric pressure on 9A should be 2 and some change, okay, like 2.1-ish, okay? And then on that second one, on 9B, it's going to be around 1.9, okay? So this is relevant to all of you as you drive cars, okay? Now, ladies, I can say this because this is going to be true of you all. Y'all are going to be going to college, okay? You're going to be out on your own, right? One of the things that you all need to have in your car, if you don't already, is a pressure gauge. So you can measure the pressure on your tires. So if you go to Quick Trip or something like that, so that you can measure that pressure. So typically, in some cars now, most cars have like a pressure sensor when it goes off, if you have like a low pressure. That's typically going to happen on cold nights. Because what's going to happen on cold nights, you're off of college, and it's like you start your car, and it's like it's early in the morning, and you're going, oh, I've got a low pressure sensor. Okay, what do I do? Just think it through. You're going, oh, right, Burkamp told me this is probably going to happen. Because it's cold, the little timmies that make up the inside of your car tire, okay, it's cold. They're not bouncing around as much, okay? So you're probably getting that low sensor pressure light because of the fact that it's cold. Because the particles just aren't moving around as much. So odds are when you drive your car, it's probably going to warm up a little bit and that pressure sensor will go off. But if you're not sure, this is why you always want to have, you can buy them at Walmart, whatever, okay, little pressure sensor gauge. You can go out and check the pressure on your tires and see what they should be. Okay, they're typically around 30 to 35. If you're not sure, there's usually stamped on the side of your tires and it'll say, here's what the pressure should be, okay? Look at the side of your tires. Here's your homework assignment. If you've never looked at the sides of your tires, it's going to say, hey, here's what the pressure should be. So just be aware of that. Don't be dependent on boyfriend, mom, dad, whoever, okay? At some point, take ownership of your car and go, okay, hey, I'm going to check the pressure in my tires. So if you do get a low pressure sensor, it's typically when it's cold because of this relationship right here, okay? There's my speed. If you were my daughters, I would make you all have tire pressure sensors. How about that? Okay. Kids always ask me, do you have kids? It's like, not that I'm aware of. I don't know. Could be. I don't know. Okay. All right. Now, so you all got that one? So on number 10, let me make sure everybody's cool with the conversions. So you've got 0.450 grams of helium, right? You need to change the grams of helium into moles of helium. So if you're a little bit rusty on your conversions of chemistry, remember you're going to put the 4 grams of helium down here and then the 1 mole of helium up there. So that's going to get you your value of N, okay? So if all goes well on that one on number 10, and you can either have pascals or newtons per square meter, it doesn't make any difference. They're the same thing. So on 10A, the first answer on 10A is around 1,000 pascals, and then the second one is around 400 pascals. Okay, so on number 10, that's kind of where your answers should be, which is really, really low, okay? Because like I said, typically right now you all are under a pressure of about 101,000 pascals. So this is like only 1,000 pascals, so this is actually a pretty low number, okay? So that isn't much pressure at all. Okay, now on number kind of 11 through 14 all hinge off the same idea. So what you all have is this chart that has all of these physical constants, these values of thermal expansion. So down here at the bottom, I've given you like these handy-dandy list of equations, right? So here's the basic idea, and again, it goes back to metals or concrete or whatever being made out of little particles that we'll name Timmy. So when metal heats up, okay, they vibrate more. And as they vibrate more, they occupy more space. And again, you can make the analogy with second graders out on the playground, okay? This morning it's like 34 degrees out, right? And if the kids were outside, they'd probably all be huddled around, right? Oh, it's cold, okay? Right? Now, if it's by the afternoon, let's say it warms up to like 70 degrees. Sun comes out, temperature goes up to 70. You can have those same kids out there, but now I can guarantee you those kids are not going to be huddled together. Those kids are going to have a lot more kinetic energy and they're going to be occupying a lot more space. So here's one of the most important things that you have to get out of these equations. All right? If you look at like that L equals L naught times 1 plus alpha delta T. Here's what's important. This is change in temperature, okay? This is not the temperature. So this only works when you have a change in temperature, okay? Listen to me. This only applies when you have a change in temperature. The temperature isn't changing, the length isn't going to change because the kids are going to have the same amount of kinetic energy. So you're only going to notice a difference in the volume or length of the kids or whatever they are when you undergo a temperature change. So this is where the units get a little bit weird. So if you look on that chart of alphas, they're all Celsius to the -1, okay? Now, again, this is not temperature, it's change in temperature. Now, there is one thing that you need to understand. If I go from 20 degrees Celsius to 30 degrees Celsius, okay, that's a change of 10 degrees Celsius, okay? Now, if I'm on the Kelvin scale, 20 degrees is 293 Kelvin, 30 degrees is 303 Kelvin, and that's also a change of 10. So here's, because you're talking about a change in temperature, a 10-degree change in Celsius is the same as a 10-degree change in Kelvin, okay? Because you're just adding numbers to it to make that conversion, okay? So if you look on like number 11, you're going from 0 degrees Celsius to 20 degrees Celsius. If you converted those into Kelvin and found the change in temperature, it would still be 20 degrees. It's just 20 degrees Celsius versus 20 degrees Kelvin. Okay, that's the only difference. So what you want to look at on number 11, so you've got L naught, which is the length of the bridge, which is 50 meters, okay, which is pretty long, okay, that's like half the length of a football field, okay, 50 meters is a pretty long piece of metal. So that's going to be a pretty big number. You're going to go through and you're going to find the value of alpha for iron, okay, that value, and different metals and different materials have different values. And then that's going to be your change in temperature. That is not your temperature, it's the change in temperature, okay? Which is going to be a key thing to understand. That's the change in temperature, okay? So there's two, if you look at number 11, I actually want two different answers on number 11. I want to know what's the final, on number 11 I want to know what will be the final length of the iron and what will be the change in length given in centimeters. So you need to have two different answers for number 11. Now, on number 11, that change in length in centimeters is going to be about 1.2 centimeters, okay? Which isn't very long. So you have this big massive length of steel, about half the length of a football field. And you're going to warm it up from basically where water freezes at 0 up to about 20 degrees Celsius, which is about 20 degrees Celsius is about 70 degrees Fahrenheit, okay? So this isn't a huge, massive temperature change. And that length is going to change about this much, okay? And you wouldn't think, well, what's the big deal? Okay, so it only changes that much. But here's the classic example. If you've ever been to St. Louis, and if you've ever seen like the St. Louis Arch, or you know what I'm talking about, okay? So it's this big massive arch that's built like this. So when this thing was actually built, what they did is they actually started and they built both sides. They built both sides going up like this, and they met in the middle. So the last thing they had to do was insert this last piece of metal. So this is how well this thing was engineered. They knew what the temperature was going to be on the day that they were going to put that in. And so they built this where it would just fit in here. Well, here's what happened. The sun came out and it heated up the arch. And as it heated up the arch, this metal actually expanded so much that they couldn't get this piece in there because the sun was shining on both sides of the arches. And that it was such a huge length of metal that both sides expanded and this wouldn't fit in there. So they called in the fire department, and the fire department started spraying cold water on both sides of this metal. And once they sprayed that on there and that metal cooled down and it contracted back, then they could put that piece in there. So it had such tight tolerances that even when that sun was shining on it, it wouldn't allow it to fit. So they had to cool it down, and then they could get that last piece of that arch up there at the top. So that's kind of important when you look at thermal expansions with water or with metal. Okay, on 13 and 14, you're looking at the change in area. So again, you've got the handy dandy little equations down there at the bottom. So you've got area equals area naught times 1 plus 2 to alpha delta t. So here's the deal. If you're looking at like a number 13. So on number 13, this is going to be your initial area, okay? You're told on that one that it's 20 centimeters on an edge, okay? So take 20 times 20, boom, there's your area. That's going to be your area naught. And the reason that there's a 2 in here, because of the fact that area is a two-dimensional quantity. That's why there's a 2 in here. The next one you deal with volume. There's a 3 in here because volume is going to expand in 3 different dimensions. Okay? So, I just leave it in square centimeters. It's just going to be easier that way because it doesn't make any difference what the units are in. So I just leave them in square centimeters. If you're really hardcore and you want to change the centimeters into meters, you can, but you can just, whatever works for you. Anyway, so does anybody have any other questions on that assignment? Are you all good?
When we convert to pascals, do you want us to like still make it, like do you want us to keep it long, like how 101,300 is, or do you want us to just shorten it?
What do you mean?
Like just round it?
Oh no, oh no.
Don't round it ever?
No.
Okay.
No. Let's say that you have 2 atmospheres, okay? And you want to change that into pascals, okay? So you're going to go 1 atmosphere is 101,300. So that's going to be 202,600. Yeah, don't round that. Keep it like that. Okay? All right. Anything else?
16.
Okay. So number 16, you're trying to figure out what that length is. So start with this, that L equals L naught times 1 plus alpha delta t. So this is more of an algebra problem than anything. So on this one, you know that it's 0.500 meters long, so you know your L naught value. Okay, you've got that. You heat it up, and it changes to 0.50068. Okay, so you have that number. You know that it's changed by 80 degrees Celsius, so you have the delta T. So the only thing you don't know is alpha. So it just turns into an algebra problem. So this is all about the sequence. So you need to divide by L naught, okay? Get this over here, divide by L naught. That leaves you 1 plus alpha delta T. Then this is what I would do. Now imagine I've got this by itself, right? So I would subtract 1, okay? And then I would divide by delta T, and then I'm left with alpha. Then once I get that value of alpha, then it's just a matter of looking at my chart and figuring out which metal has that value of that thermal expansion. Okay? Yeah, so it's just an algebra problem. But that's one thing that you can, because each metal kind of has its unique thermal properties of expansion, so if you don't know what it is, that's one thing that you can do to identify a metal, is figure out what that is and go, okay, well, it's clearly going to be magnesium, iron, whatever that is. Okay. All right. Any other questions? At all? Ray Ha, you good? Okay, going once, going twice. So, okay. All right, I've got to go get a cup of hot water, and I'll be right back. Stop this for a second. Okay, so this is a cup of very, 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 very hot water. And I had it in the microwave. And so, what I'm going to do, this is what's known as a Stirling engine. So, I'm going to put this on here, and this is going to take a while for it to work. So, what I'm going to demonstrate is that when things are heated up, they contain energy that we can harness. So, I'm going to take this and I'm going to spin this, and I got to remember which direction it spins. Okay? So, it's going to take a while. But what's happening is that they've got a series of cams that are here. And this one is hooked up to a diaphragm that is making, if you look on the inside here, there's a little piece of foam that goes up and down. So what's happening is that this whole system is heating up. And as it's heating up, basically how your car engine works is that your car engine takes in gasoline, which has a certain amount of chemical potential energy. You fire the engine, that gas explodes, and it does work, and it drives the piston down. And then that's what allows your car to work. So you take in a certain amount of energy, you use that energy to make you go down the road, and then you lose a lot of energy to heat. And the same thing happens to us as human beings. We're about 25% efficient. So what that means is that if we consume like 100 units of energy, like a calorie of, if you've ever tried to watch, how much calories do you consume? Calories is the measure of food energy. So if you consume 100 calories of energy, you only actually get 25 out of that are functionally able to, that you can use. Okay, the other 75% are basically wasted as heat, because that's, you're just little thermal engines, and you're burning and you're radiating heat all the time. So what happens with this is that, let me get this thing going, and it's going to take a while, is that it's going to take that thermal energy that's actually one of the fastest that it's ever worked. Okay, so here's what's happening. So this machine, we'll represent the machine as a box, is that it's taking in a certain amount of thermal energy from the cup of hot water. Okay, so this is just really, really, really hot water. So it's taking in this energy. And what it's doing is that it's using some of that energy to do work. Okay? So that work that it's doing is making that energy, is making that propeller spin. So we're going to do some of that to do work. Now, we're also expelling some of that energy out as thermal energy that we can't use. So the whole idea being is that when you heat stuff up, it has the capacity to do work. So this is what typically, like sort of a solar panel array. This is also what we use to generate electricity, because what we do is we heat up water, we boil it, it turns into steam. That steam has a lot of energy. That steam spins a turbine. The turbine spins a generator. The generator generates electricity. We ship the electricity to Mays High School. Mr. Burkamp can make toast in the morning, okay, before you all get here, or run a projector or whatever. So the whole idea being is that when you heat up water, whatever that is, it's going to contain a certain amount of thermal energy. So the efficiency of an engine is determined by how much energy that you take in, how much can you do out of that, and then how much gets wasted. So we're all about 25% efficient. So if you consider this being you as an engine, okay, you consume 100 food calories, you're only going to be able to use 25 of that to do work, and then the other 75 gets wasted as thermal energy, okay? But here's the idea. When things are heated up, they can do work. So this will run for probably for about another 2 or 3 minutes, okay, as this thing continues to go. All right. So let me hand out this sheet of lecture notes so that you all have those. Riley, this is somehow your fault because I had to get organized.
Okay.
Okay, so what happens here is, let's just start at the beginning. So here was my cup of coffee, or cup of water, and I had water in it, and I had it in the microwave. Okay, so at the very beginning, let's talk about how microwaves work. Microwaves work because of the fact that they emit photons. Photons are little bundles of energy. And you can't see microwaves because it isn't something that our eyes can pick up, because microwaves are actually very long wavelength. Okay? We can't see them. Because if we could, then we could actually see, if you could see microwaves, then when you were heating up food in your microwave oven, you could actually see not only you would see it like a light. You would see those microwaves being emitted, which would be kind of cool. But we can't see them, and that's okay. We can actually see a very narrow band of the electromagnetic spectrum. So the cool thing about microwaves is that when they hit water, they make the water molecules vibrate. Okay? And when these water molecules vibrate, that generates heat. So it's like you're making these things rub together very, very violently. And when that happens, you generate heat, and the water now got heated up because all the little water molecules were in there. They were being bombarded with microwaves, and they started to flip out. And as they vibrated, they warmed up, okay? And they have a lot more kinetic energy, which is why this thing feels really, really hot to my hand right now. Okay, so got the idea. So if we want to calculate how much energy that takes, so on your sheet, you've got this that Q equals M delta T C sub P. In Chem 1, you might have seen this, but I'm not sure, because like last year with the whole virus thing, some got to thermodynamics, some didn't, so I'm going to assume that you all did. Now, so this value of Q, this is your energy. Okay? Now, that is not temperature. Okay? Energy, that value of Q, is going to be how much energy is contained within the cup. It isn't just temperature. It's the entire amount of thermal energy that's inside that cup. Now, in physics, this M is going to be your mass, and that's going to be in kilograms. This is going to be your change in temperature. Okay, again, this isn't temperature, but it's your change in temperature. Now, the C sub P is what we call specific heat. So, on your the sheet of paper that has all your thermal constants on it. So over here you've got, up here at the top it says specific heat of various substances at 20 degrees in 1 atmosphere, like now. So notice that these units are joules per kilogram degrees Celsius. So what this number means is this. If I have a kilogram of water, okay, kilogram of water, so equivalent to this. Notice that the specific heat of water is actually one of the biggest ones, and that's 4,186. So that's 4,186 joules per kilogram degrees Celsius. So let me kind of give you some perspective on just that particular number. So here's a kilogram of water. Okay, you all have an idea of what a kilogram is. You all work with masses. Here's a kilogram, right? 4,186 joules. So let me give you some perspective. Let's just make the math easy. So let's say 1 kilogram weighs 10 newtons. It's actually 9.8, but let's say that it's 10. Okay? We'll round it up a little bit. We'll call it 10. So if I take this 1 kilogram mass, which weighs 10 newtons, and I lift it up to a height of 1 meter, I do 10 joules of work. Okay? I take 1 kilogram mass, weighs 10 newtons. I lift it up, boom, I just did 10 joules of work. So if you take 4,186 and divide it by 10, you get about 420. Okay? Roughly. You get about 420. So for me to take 1 kilogram of water, okay, like this, and I'm going to change it 1 degree Celsius. Maybe I'm going to raise it from 20 degrees Celsius to 21 degrees Celsius. Okay, that isn't much of a change. I'm just going to change it 1 degree Celsius. That would be the same amount of energy it would take for me to lift this thing up 420 times. So if I could do this, start right here, lift this up 420 times, that's how much energy it would take to take 1 kilogram of water and just change it 1 degree Celsius. Okay? Now, look at this equation. Notice that this is all multiplied together. So, think about this. Oh, okay. If I just have a cup of water versus like 5 gallons of water, well, 5 gallons of water is going to take a lot more energy to heat up than 1 little cup of water is going to. Oh, okay, so it's dependent upon mass. Change in temperature. If I just want to raise the temperature of the water from 5 degrees to 10 degrees, okay, that isn't much of a change. Oh, okay. That's not going to take much energy. But that cup of water, it took a lot of energy because I had to change it from room temperature, which is about 20 degrees, up to about 90 degrees. So when I was heating that water up in the microwave, that took a lot of energy because I had a big temperature change. Now, the other value is specific heat. So this is why you have this chart. And you notice on this chart that water is actually the biggest one on here. Water has the largest specific heat. So, which is both good and bad. So, when you all get out on your own, okay, another life lesson. Hot showers are nice, okay? Don't get me wrong. I spent 2.5 years of my life taking room temperature, or taking like cold showers when I was living in Africa. I like a hot shower, don't get me wrong. But to heat up water takes a tremendous amount of energy. So if you all get out of college, you get your first job, you're living in an apartment, okay, you're paying your own electrical bills. And if your electrical bills are really, really high, and it's like, wow, but I like taking really, really long hot showers, okay? Well, number one, environmentally, it's a train wreck because you're wasting a lot of water. Number two, you are wasting a lot of energy because to heat that water up, because water has such a high specific heat, that's going to take a lot of energy to heat that water up. So if you're out on your own and your electrical bills are too high, your utility bills are too high, quit taking, half an hour long showers, okay? Because you're wasting a lot of energy just heating up water. Okay, so this is how this would play out. So let's say I've got my little cup of water here, and let's say that I want to heat it up. So here's my cup of water, right? And let's say that's about a quarter of a kilogram of water. So I'm going to figure out how much energy it's going to take 200.25 kilograms. And let's say that I want to heat, that water was about 20 degrees when I started, and it's up to about 90 degrees right now. So my change in temperature is going to be temperature final minus temperature initial, just like we've always done before. Okay, so that's going to be 90 minus 20, which is going to be 70 degrees Celsius. Okay, so there's my change in temperature, 70 degrees. And then I've got that specific heat of, somebody get out a calculator because I'm just making this problem up, and 4,186 joules per kilogram degrees Celsius. So somebody take 0.25 times 70 times 4186. What'd you get, Riley?
73,255.
73,000 what?
255.
So 60 joules. Okay? Now again, to give you some perspective on this, okay? If you consider me taking this and lifting this up one time, that's like 10 joules. So if I were to take, if I wanted to use that equivalent amount of energy, that would be like me taking that 1 kilogram mass and lifting it up 7,326 times. So I would have to take that, lift it up, and if I could harness that energy, this is how many times I would have to lift it to get that amount of energy. Okay? So that's a tremendous amount of energy. Now, keep in mind, that was just one little cup. Okay? It was just one cup that I heated up. So if you look at, you're in the shower and you're going through gallons upon gallons upon gallons of water, okay? That's a tremendous amount of energy that was used to heat up that water. And again, that's the energy just for a cup of water, okay? That isn't gallons upon gallons upon gallons of water. It's just for one little cup of water. So, now, the other thing that's going to happen, and this is what the Stirling engine did, is that, so that's how much energy that I put into this thing. Now, as it cools down, because if I let this sit out here for a while, that temperature is going to drop because that energy is going to radiate back out. So as that energy radiates back out, temperatures begin to drop. So that's also then how much energy is given off as that cup of water cools down. So that's how much energy that we put in to get it to 90 degrees Celsius, but then when it cools from 90 degrees Celsius back down to 20 degrees Celsius, that's also how much energy is going to be given out. Okay, so when you look at calculations of Q, this is one of them, okay? So this is taking a substance, heating it up, and the only thing that you're typically going to change are these specific heats. So notice that like your metals, aluminum, copper, glass, okay, they have a certain amount of specific heat that's much lower than water's, okay, which is why it's easy. You put a pan on a stove, oh, that pan heats up pretty quickly because of the fact that the copper has a low specific heat. It doesn't take much energy to change the temperature of it. Now, I do want to point out one thing. Now, this is going to be important once we do these big calculations. Water exists as 3 different phases. It exists as a solid, otherwise known as ice, a liquid, and then as steam. Okay, so if you boil water, it turns into steam, and that steam has a specific heat. So one of the things I want to point out is that if you look on this sheet, There's 3 different specific heats of water. You have the specific heat of ice, you have the specific heat of liquid water, and then you have the specific heat of steam. So you only use the 4,186 if it's liquid water. If it's ice, you use a different specific heat. If it's steam, you use a completely different value of specific heat. Okay? So you have to keep in mind water is not always 4,186. It depends upon what phase it's in. Okay? All right. With that said, so now we're going to do this big, massive, long calculation. Okay? And you're going to see how this deal plays out in terms of different phases and changes and things like this. So here's what we're going to do. We're going to start with a half a kilogram of ice. Okay? And that's at, let's say, minus 5 degrees Celsius. Okay? So you get out a chunk of ice, half a kilogram, which would be about, the same volume as about about half of this. Okay? Right? So you're going to have this chunk of ice, half a kilogram. And here's what I want to do. I want to do a couple of different things. I want to warm it up to 0 degrees Celsius, because eventually I'm going to melt this ice, okay? Well, ice melts at 0 degrees Celsius. So the first thing I have to do is when I get it out of the freezer, right, I've got to warm it up from minus 5 to 0, because it's not going to start to melt until it reaches 0. So the first thing I have to do is that I'm going to change the temperature, okay? I'm going to change it from minus 5 degrees to 0. That's the first thing I'm going to do. Then I'm going to melt it, okay? So when I melt that water, that's going to be a phase change. I'm going to go from a solid water, otherwise known as ice, into a liquid, okay? So I'm going to melt the ice, right? Now here's what's going to be important. When I melt this ice, I'm not changing the temperature of the ice. I'm changing it from a solid into a liquid. So I'm breaking the bonds that hold these water molecules together, because solid water, otherwise known as ice, is just formed from these water molecules being locked in place. Okay? So what I have to do is I have to break the bonds that hold it together as ice, so that then they can move past each other and be a liquid. Now, if you think about it, if you look at most of the substances that you deal with in your life, okay, from the time that you all were born, there's actually very few liquids that you deal with, if you think about it. Most of the substances that you deal with are solids, okay? Your book, your paper, your car, okay? Or they're gases. Oh, we have an atmosphere. We kind of breathe that in. That's kind of a cool deal, okay? But if you look at liquids, there really aren't that many liquids other than water. Okay, yeah, you have milk. Well, that's basically water, okay? All right? You know, you have blood. Okay, well, that's mostly water, okay? Or a large percentage of it is water. So we really don't have that many substances in your life that are liquids. And liquids are cool because they have a unique ability to be held together as a liquid, so they remain as a liquid, but they can move past each other, okay? So there's this balancing act, because if the bonds are too strong, it exists as a solid. If the bonds are too weak, they break apart and they exist as a gas. So liquids are like in this Goldilocks zone of bond strengths, so it'll hold it together, but you can still move around. So it's kind of like a relationship. So, you know, if you're like in a liquid relationship, okay, you're held together, but you're fluid, okay? You can move around, right? You're not locked in place. Now, if you're in a relationship where it's solid, like, we're locked together, okay? It's very stifling, right? You can't move, it's like you're locked in place. Like, oh, this sucks, okay? I'm outie. I at least have a liquid relationship. Now, if you go to a gaseous relationship, you bounce into each other every once in a while, but there's no real bonds that hold you together. Okay? So it's like, hey, where are we at in our relationship? Are we a solid, are we a liquid, or are we a gas? You know, what's going on here? So you can apply that to a physics perspective. This is why I'm not a counselor, by the way, because I'd be the... So, you're having problems. What phase are you in? Are you in a solid? Are you in a liquid? Are you in a gas? Where are you at here? You know, where do you want to be? What can we do? Okay. But here's what's going to be important here. Okay? Listen to me on this one. I'm going to put energy into the system. I'm going to break bonds, but I'm not going to change the temperature. Okay? So when you have a phase change, listen to me. Energy is going to go in, but I'm not going to change the temperature. Okay? That's going to be a key thing. Now, then I want to take water and I want to warm it from 0 degrees up to 100 degrees Celsius. Because now I want to boil the water. Okay? So I've taken ice at -5. I'm going to warm it up. I'm going to have to put energy in to get it to 0. I'm going to have to put more energy in to melt it. Then, once it's all melted, then I'm going to warm it up to 100 degrees Celsius. Okay? So now I'm going to change the temperature. So, I changed the temperature, I went through a phase change, and then I'm going to change the temperature again. Now, the next thing is that I'm going to boil the water. Okay, so y'all have been in labs, y'all have boiled water. Okay, you all hopefully maybe made macaroni and cheese or boiled pasta or something like that, right? You put the water on there, it begins to boil, right? So then I'm going to boil the water, and I'm going to change it from liquid water into vapor. Okay? Now again, this is going to be a phase change. So now I'm going to put energy in, and now I'm going to break the bonds that hold the water molecules together. So now they're existing as these separate entities. Okay? Because when you know, water is H2O. When you boil water, you don't separate it into hydrogen and oxygen. Okay? You don't do that. You're just breaking apart the individual molecules that are holding them together. Okay? But again, here's what's going to be important. I'm going to undergo a phase change, but I'm not going to change the temperature. Okay? So this, when I melt the water or when I boil it, I'm not going to change the temperature, but I've got to put energy into it. Then the last thing I want to do is I want to take that steam that's at 100 degrees and I want to heat that up to, like, I don't know, maybe 105 degrees. Okay? So, I'm going to go through 5 different changes. Okay? Count them 5. I'm going to warm the ice. I'm going to melt the ice. I'm going to warm up the water. I'm going to boil the water. And then I'm going to warm up the steam. Okay? So I'm going to go through a total of 5 different phase changes. Okay? Count them 5. So, let's start with the first one. So anytime you use a change in temperature, you're going to use M delta T C sub P. So I've got a 1/2 kilogram. Okay, there's that. Now, my change in temperature is going to be 5 degrees because I'm going to go from -5 Celsius, I'm going to warm it up to 0. Okay, so my change in temperature is going to be 5 degrees. Okay, got that. Now, Riley, get that calculator out because I'm just making up this problem. Now, I've got to use the specific heat of ice. So I'm going to come to this chart. I want to find the specific heat of ice, which is 2100. Okay, so that's 2100 joules per kilogram degrees Celsius. I'm not using the 4186 because I don't have liquid water. I have ice. Okay, that's why I'm using this 2100. So, Riley, what'd you get?
5,250.
5,250 joules. Okay? Now, all I've done is just warmed up the ice. I haven't melted it yet. Okay? But I got to get it up to 0 before it can begin to melt. Okay? So at this point, imagine this. I've got ice at 0. So what's happening here is I'm going to look at a different kind of graph. Energy and actually, let me reverse that. Okay, so here's what I did. I started at minus 5 degrees Celsius, and I put energy into the system, and I warmed it up to 0. So I put energy in, and that energy is warming this stuff up. So these particles are getting more and more kinetic energy, okay? Now, at this point, I have solid ice. Now I need to melt the ice. So what's going to happen is that this line is going to become horizontal. So what's going to happen is that I'm going to dump energy into the system, but I'm not going to change the temperature, okay? Because I'm going to break the bonds that hold it as solid so that it can move together as a liquid. Now, on your equation sheet, okay, back here, you have 3 different calculations of Q. So if you look at the back side of your equation sheet, so you've got that Q equals mc sub T delta T. That's the one we just dealt with, okay? Then I'm going to have Q equals MLF, which is latent heat of fusion, and Q equals MLV, latent heat of vaporization, which are fancy. These last 2 are what you're going to use for phase changes. So what's going to happen here is that now I have ice, and I want to melt ice. So what I'm going to do is I'm going to use Q equals MLF, because fusion is like fusing particles together, okay? So I'm going to have the 1/2 kilogram. Now, I want you to pay attention to what happens to the units. So if you look on this chart, okay, down here, notice that down here about halfway down, I've got latent heat of fusion and I've got latent heat of vaporization. So notice with water, that's 3.33 times 10 to the 5th, and look what happens with the units. That's joules per kilogram. Notice that on this latent heat of fusion, notice that there's no degrees Celsius, okay? The reason that there's no degrees Celsius is because we're not changing the temperature. The only thing that determines how much energy this is going to take is how much mass that I have. Now, obviously, you know, we had that big snowstorm last weekend, okay? That was a whole bunch of ice that fell. Wow, we melted it. That took a tremendous amount of energy, thermal energy from the sun, because if we didn't have the thermal energy from the sun, that ice would have never melted. So, if you look at how much energy that took to melt that ice, that's going to be a lot of energy because we had a whole bunch of snow that fell. Those tiny little bits of ice, basically, is what snow is. So, Ryan, take 0.5 times 3.33 times 10 to the 5th.
166,500.
6,500 joules. Okay, so here's what's important. I'm dumping this energy in, okay? But I'm not changing the temperature because I'm breaking the bonds that hold the water molecules together. Now, look at the difference in this. This is like 10 to the 3rd. This is 10 to the 1, 2. Yeah, this is 10 to the 5th. So this is 10 to the 3rd, this is 10 to the 5th. So this is like 100 times more energy to melt the ice than it does to warm up the ice. So it takes it, this is why it's hard to make ice, okay? If you want to make, mom says, hey, let's make ice, here's your lab for the day. To do that, if you reverse this process and you have water and you want to make ice, this is how much energy that you would have to take out of it to take liquid water and change it into ice. If you have ice and you want to make water, this is how much energy that you have to add to it. That's a lot of energy. Okay, so here's the story. At this point, we have liquid water that's at 0 degrees. Now, we only have 3 more calculations to do. So if you look at what's going to happen here, then the next calculation is that I need to take that water at 0 degrees Celsius and I need to warm that up to 100 degrees Celsius. Okay, so now I'm going to go from liquid water here up to 100 degrees. So now I'm going to change the temperature. So now I'm going to go back to using 0 up to 100. I'm going to go back to using m delta t c sub p, because now my energy is going to go to make the little timmies vibrate a lot more. Okay, so now I'm going to increase the temperature. So this is still going to be that half a kilogram. My change in temperature is going to be 100 degrees Celsius. Now I'm going to use the specific heat of water, which is 4,186. So now I got 4,186 joules per kilogram degrees Celsius. Now, notice that now I'm back to using degrees Celsius here, because this amount of energy is dependent upon the mass, the specific heat, and the change in the temperature. Okay? So, Riley, what'd you get?
209,300.
209,300 joules. Okay? So that's a lot. Okay? That's a lot of energy. So this is, again, this is like 10 to the 5th. So this is 10 to the 5th. Okay? That's a lot of energy that it's going to take to heat up. And again, this is only a half a kilogram of water. Okay? This isn't like it's a huge amount of water. It's like 500 grams, right? This is like a pound of water. This is how much energy it's going to take to boil that water. Okay. So at this point, visualize this. You're looking at a beaker. At this point, your temperature gauge is reading 100. Now we're going to begin to boil water. So now we're going to go through a phase change again. So now we're going to boil water. So now we're going to take liquid water and we're going to change that into vapor. Okay? So now, on my chart, I'm going to use the latent heat of vaporization of water, right? So I'm going to use Q equals M times the latent heat of vaporization, which is going to be a half a kilogram times, I should have this memorized, 22.6. Now, I want you to look at this. To boil water, this is like 22.6 times 10 to the 5th, okay? To melt ice, that was 3.33 times 10 to the 5th. So if you compare 22.6 times 10 to the 5th to 3.33 times 10 to the 5th, it takes a lot more energy to boil water than it does to melt ice, okay, by like a factor of 10. So it's much more energy intensive to boil water than it does to melt ice, okay? So if that was the case, like if ice took that same amount of energy to melt, snow would last a lot longer because it would take a lot more energy to melt that ice, okay? Which would be kind of cool because your ice then in your drinks, you know, your ice could absorb a lot more energy and keep your drinks cold longer because it would have to take a lot more energy to melt that. But here's what I want you to see. Boiling water is much more energy intensive than melting ice. Okay. So, you got that number. What'd you get out of all that, Riley? 11? What'd you get? 0.5 times 22.6 times 10 to the 5th. What'd you get?
1,130,000.
1 million what?
130,000.
130,000 joules. Okay, so which is like 3, 4, 5, 6. Okay, so here's our last calculation. Now we have this vapor that's at 100 degrees. Now we need to take that vapor and we need to warm it up from 100 degrees, I don't remember what I even said, up to 105. Okay, so now we're going to heat up the vapor. So here's our last calculation. So M delta T C sub P. So I've got a half a kilogram of steam. I'm going to change that temperature 5 degrees. But now I'm going to use the specific heat of steam. So I'm going to come over here and I'm going to use that specific heat of 2000. I'm not using the 4186 because it's no longer liquid water. So I'm going to use, what is that, 20 or 2000 joules per kilogram degree Celsius. And what do you get, Riley? Hopefully 5,000. Okay, now here we go, Riley. Here's your last and final step. So, here's what we did. On this graph, we did this. We took ice at -5, we warmed it up. We melted the ice, we warmed up the water, we boiled the water, and now we warmed up the steam. So, here's what I want you to do, Riley. I want you to add together all 5 energies. Okay, the 5,000 plus the 1.13 times 10 to the 6 plus the 209,300, and add up all of that and let me know what you get.
$1,516,050.
1,500,000 what?
16,050.
50. That's a lot of energy. So that's to take a half a kilogram of water and raise it, melt it, warm it, boil it, warm up the steam. And that's just for a half a kilogram of water. So this is why making electricity by boiling water is so energy intensive, because water has such a high specific heat, and this is the advantage of like solar arrays, because you don't have to waste all that water. You just get a direct conversion of that energy from sunlight. Okay, I'm done. So if you want to go ahead and start working on this assignment, you can basically work, hold on. You're welcome. So at this point, you can, on this assignment, this isn't due until Monday, but you can basically do everything up through probably about number 8. So if you want a head start, you can. So I'm done. We'll call it a day.